First of all, I would like to thank the organizers and particularly the session chair for giving me the opportunity to present my work, and I'm really, really sorry that I cannot be in Bodrum right now. Okay, so the story I'm going to tell you today is about a simple model for a system that is a charge insulator, but shows topological features in its thermal transport, and this is basically a model for a chiral spin liquid. The work is summarized in a paper with my graduate student Pasha Tikhonov, and here's a reference for the publication. So this is the outline of my talk. I will start with some brief introduction to the concept of a chiral spin liquid, and I'm going to advocate the idea that this is a system where in principle we can see a charge neutral analog of a topological feature known from charge conductors, and that is a quantum Hall liquid. Then I will briefly mention thermal Hall effect measurements just to show that there are some interesting results already there in the literature that such measurements are possible. And then I will focus on our work, which is a model for a Kagome strip, which serves as a minimal theoretical model which captures the main features of such an exotic state, and I will discuss the quantum phases that you get from the model and how they are signatured in the thermal Hall conductance, and in particular how it is tunable by an external magnetic field. So let's start with a brief introduction. The previous speaker already discussed the concept of a spin liquid, the quantum spin liquid. And that is an exotic state of matter that you can get in platforms that have the feature of frustration. So, for example, if you take a frustrated lattice like a Kagome crystal as a prominent example, and try to put an anti-ferromagnet Heisenberg model on such a lattice, you get a frustration. Classically, you get high degeneracy, macroscopic degeneracy of the ground state, and hence quantum fluctuations resulting from the fact that the various components of a spin are non-commuting object. This can give rise to some new kinds of ground states. One possibility is that you can still get not a magnetically ordered state, which is unfavorable, but rather some kind of a valence bond crystal, which locally captures quantum fluctuations, but still breaks the translation symmetry of the crystal. But in a more interesting possibility is that such a quantum state, such a valence bond is itself fluctuating and generates a state that we generally dub as spin liquid, and its main feature is that there is no order. You have basically you have some low energy excitations that can constantly flip the spin, and you can think of it as some kind of a liquid, and that suggests a particle description of some kind of itinerant particles, either bosons or fermions, that carry the the spin degree of freedom. So to adapt a model that has such a particle description, what you need is some mapping between the original spin operators and some particle entities. So such a mapping is usually very easily possible in one-dimensional systems, but you can also generalize it to higher dimensions. And there's some mapping to spin-on creation and annihilation operators. This transformation is, by the way, typically highly non-local, so it's not a simple mapping, but it's providing some notion of a quantum particle. And then there is a spin operator SZ, which serves as a density operator for such spin-ons. And as a result, the Zeeman magnetic field serves as a chemical potential which can control the occupation or the density of the spin-ons. Now, similarly to the spin-on density, one can also define a spin-on current operator, and that current operator can be related to an object like this that describes spin propagation, so S cross S on neighboring sites. Now, since we introduced a particle language that has density, it has current, it has a chemical potential, we also would like to have an analog of a magnetic field. And this fictitious magnetic field is something that should couple to the current in a similar way as magnetic field does in charge conducting systems. So perhaps one of the first proposals, I think, for such an object was introduced in this famous work of Kallmeier and Laughlin, where they show that on a triangular lattice, one can map the spin Hamiltonian to some tight binding model of particles. However, this tight binding involves a gauge transformation, and as a result, they argue that you can have an analog of the mu equal to bosonic quantum Hall liquid in such a system. Now, however, in this particular realization of a spin liquid state, of a chiral spin liquid state, the gauge transformation is such that it can only take values that are plus minus 1. So there is no arbitrary flux. If you think of the plaquette in the triangular lattice, the flux, the fictitious flux that you have is in fact just half of the flux quantum. So there's no tunability here. It's just something that comes from the geometry of the lattice in this mapping. So it would be nice to have an alternative way of generating a fictitious flux, which can take arbitrary value and tune possibly other kind of quantum Hall-like states. And such an object exists, and this is the Dzielozinski-Moriya interaction, which was shown in many talks in this conference. This is its form, so there is some constant vector originating from spin, so this effect essentially originates from a spin orbit coupling, and since I already mentioned that this operator S cross S can be related to an analog of a current for spin-ons, therefore this D can be thought of as some kind of a vector potential, and in principle it can be engineered to have different values and create something that looks like a constant magnetic field. So yeah, so there was already a mention in the literature that in the presence of such interaction, you may develop a state which has a chiral order parameter coming from a 3-spin ring exchange, and for that to occur, you need to break both parity and time reversal symmetry. So okay, so now let me just briefly mention what is a thermal Hall effect that we are going to suggest as a signature for the state I will be studying. It's basically the analog of the Hall effect for charge system, but here this is instead of charge current, you have a thermal current perpendicular to the temperature gradient in a magnetic field. And to generate such an effect, you need some kind of excitation that whose dynamics is similar to a particle in a magnetic field. So since I don't have much time, let me just mention briefly that there were some magnetic systems that where a thermal Hall effect was measured, and I don't want to discuss the result except for mentioning one of them that is obtained in the alpha routinate, a candidate for realization of the Kitaev spin liquid model, where an interesting observation, which I think to this date is still controversial, is that in some regime of a magnetic field, they see a quantized plateau in the thermal Hall effect, and that suggests as an indication of having a chiral Majorana mode. Okay, so our model actually does not try to address this particular system, but this behavior where you see a narrow plateau can emerge in our model in some constellation, and let me now come to describing our work. So the idea was the following. We introduce a tractable minimal model, which is actually quasi one-dimensional, but it has the minimal size to mimic what happens in the full-fledged two-dimensional case, and it's a Kagome lattice structure, Kagome strip, and we assume that there are two external fields. One is the DM interaction, which is breaking explicitly the inversion symmetry, and it assumed to be dictated, and there's an external magnetic field that is tunable, and that contributes to the breaking of time reversal. And therefore we have the conditions for creating a chiral spin liquid order parameter. Okay, so the reason that we consider the quasi one-dimensional system is that it can be analyzed theoretically using basically bosonization, the tools that are available for one-dimensional systems, and also explicitly calculate the thermal Hall effect. And the idea is the following: we consider a strip of an infinitely long Kagome crystal, which has a finite width of, and the way we view it is we introduce some distortion so that we can imagine that this is essentially three chains, okay, 3 spin 1/2 chains that are meandering along these strong bonds, and they are weakly coupled, and these couplings introduce a richness of different phases. Now, what are the notations? So these strong bonds in black represent XXZ spin interaction, just the standard Heisenberg-like, and these circles represent the DM interaction, and there's a fixed coefficient D. And we also introduce a Zeeman magnetic field, and this is going to serve as a tunable parameter. So I think I will better, I'll better skip the details of the theory because I don't have time. Let me just mention briefly what is the idea. It's mapping, it's basically mapping this three-chain system into three-coupled Latinger liquid wires via bosonization by mapping the spins to bosonic operators. And we introduce the coupling between them, and these correspond to some nonlinear terms, and we apply a normalization group to study what kind of phases we can have under different choices for the parameters. Okay, let me just go directly to the main result, and that's a phase diagram. So in this phase diagram, I plot two parameters. The horizontal axis is parameter K, which is a Latinger parameter in the theory model. In reality, it corresponds to some anisotropy of the crystal. So
please note you have 2 minutes left.
Oh, okay. So this is basically the main result. So, the other axis is a magnetic field, and we basically get three phases here. One is a valence bond crystal, and one is just a spin metallic state, and the most interesting one is really an analog of a fractional quantum Hall state where we can define a quantum Hall effective filling factor, which is the ratio of magnetic field to this DM interaction D. So if we tune a magnetic field through our phase diagram in a regime of parameters where we can go through all three phases, this is how kappa xy should look like as a function of B. The valence bond crystal will be a spin insulator, there will be a spin metal phase, and there will be a quantized plateau in a narrow range, which is centered around a very particular choice of a magnetic field where there is a commensurate filling factor or commensurate ratio between an effective flux and effective density of the spinons. So let me summarize. We studied a model for spin half chain on a Kagome strip, subject to a DM interaction and an external magnetic field. We identify three phases, and the one that I want to emphasize correspond to some specific range in parameter space where kappa xy is going to be quantized by one quantum of the thermal transport, and the condition for that is that the magnetic field is close to which is the central of this plateau, is when the magnetic field is such that its ratio to the DM interaction gives you a particular fraction. In this case, it's the fraction 1/2. let me just emphasize that in a charged quantum Hall liquid, the filling factor is defined as ratio of electron density to magnetic field. Here the magnetic field appears in the numerator. That serves as the chemical potential or the doping of spin-ons, if you like, whereas it's the M interaction in our model that serves as the fictitious magnetic field. So thank you for the attention, and sorry for taking 2 more minutes.
So thank you very much for your interesting presentation. So we have a couple of minutes for questions. So when you consider, the thermal transport, what are the particles which carry thermal current? So these are spin-ons in your
These are spin-ons, yeah.
So you
in
don't involve
case,
any phonons. So they're not
no, so of course, yeah, so phonons can contribute to heat transport but we are looking at the thermal Hall conduction. So so of course phonons can also give some contribution to that, but the thermal Hall current is typically not carried, at least to leading order, by phonons, right? Because they have no chirality. So it's really the spin-ons, and there are some edge state modes that contribute.
Well, okay, so of course the phonons, they don't have spin and chirality, but they can scatter on some magnetic objects which are chiral, and that would also could cause a thermal Hall effect, or?
That's definitely, you're completely correct, and in fact there were some papers in the literature that claimed, that there's a spin liquid state where phonons can explain a lot of it, but I'm basically assuming you of course need to do some analysis to separate them, and one possibility is to look at magnetic field dependence. So magnetic field dependence will be very different for spin-ons and phonons. Moreover, the systems I'm thinking of as realization are really such that the spin-on contribution is expected to be dominant, but yeah, of course, in practice, it requires some analysis how to separate them, and it can affect the transport.
Okay, so thank you very much.